Welcome back to Basic Mathematics. In this video, we're going to be looking at simplifying variable expressions. As we've seen previously, working with variable expressions when you know the value of a variable is something that's fairly straightforward to do, but can be a little bit tedious, especially if a variable shows up multiple times in an expression. So, the power of algebra, the reason that mathematics is useful as a problem-solving tool, is that we can abstract away and not worry about the value of a variable and try to cheat, in a sense, to figure out ways of performing some calculations beforehand. When it comes to evaluating an expression one time, this is really not all that useful. The thing that I want you to keep in mind is a formula that needs to be used over and over and over again, possibly several times a day, or in the case of computer programming, several times a second, in order to perform some goal. The simpler you make the calculation, the faster you can do it, the more often you can go through it, the more you can get done. So with that in mind, let me get my head out of the way, and let's take a look at the two rules of simplifying expressions. The first rule is called the distributive property. The distributive property says that for any three numbers, a, b, and c, if you want to multiply a times the sum of b plus c, you get a times b plus a times c. This is not a property that we have named so far in this course, but it is very important because it's how longhand multiplication works. If you want to multiply, let's go with something relatively straightforward. 23 times 7. Well, using the distributive property, we can think of 23 times 7 as 7 times 23. And then in a very convoluted way, we can write that as 7 times 20 plus 3, which is important because the distributive property tells us that that's 7 times 20 plus 7 times 3. Seven times 20 is easy to calculate, you get 140. 7 times 3 is easy to calculate, you get 21, and you can add those things together. In longhand multiplication, we take 7 times 3, we get 21, we write the 1, we carry the 2. We get 7 times 2, which is 14, and add 2. The 14 and 2 gives us 16. So that's the process. We never write it out in longhand like this, but it absolutely works. But the reason that the distributive property is so valuable to us at this point is we might be looking at an expression like 3 times 7x minus 5. Now, subtraction is really addition in disguise, so this is 3 times 7x plus negative 5, and that is important. If we need to evaluate this, we substitute in the value for x. We multiply times 7. We take that result and subtract 5. We take that result and multiply by 3. Multiply by 7, subtract 5, multiply by 3. That's 3 steps. But watch what happens when we use the distributive property. 3 times 7x plus negative 5 is 3 times 7x plus 3 times negative 5. And 3 times 7 is 21. And the rules of algebra tell us the next thing we should do is multiply 21 times x, although we don't quite know what that is. Luckily, that 21 times x is going to sit for a little bit because the step after that would be multiply 3 times -5, which is -15. And then only after that would we subtract. At this point, because we don't know what x is, there is nothing we can do. I suppose we could rewrite this as 21x minus 15. But because we don't know what x is, we have to multiply 21 times x before we can do anything else. This is as simplified as the expression gets. And as I said before, if all you're trying to do is evaluate this expression once, you haven't really gained anything. But if this is an expression that you have to evaluate multiple times, instead of having 3 operations to do, we now only have 2. The numbers are a little bit bigger, it's a little bit more annoying. There's an argument that could be made for this particular problem, whether that's better or worse. But if your job is to program things into a computer, programming 2 operations takes less work, it is less prone to error than trying to program 3 operations. So once you're sure that this is correct, you can do this 1,000 times and save yourself 1 step each of those times. So that is a powerful and useful tool. But it turns out that the distributive property is actually more powerful in a behind-the-scenes approach. Consider this expression, 3 times x plus 5 times x. Order of operations says that the first thing I need to do is multiply 3 times x. Since I don't know what x is, I'm out of luck. The next thing I need to do is multiply 5 times x. Since I don't know what x is, I'm still out of luck. Then after that, I add those 2 numbers together, and I don't know what either of those numbers are. So according to the order of operations, there is nothing I can do here. But because I have the distributive property in my back pocket, I can be a little bit sneaky. Notice that if I distributed x times the quantity 3 plus 5, I would get x times 3, or 3x. I would get x times 5, or 5x. So in this step, I use the distributive property, but backwards. And the reason this is so valuable is that now, according to the order of operations, the first thing I have to do is add 3 plus 5. I know that 3 plus 5 is 8. Then I multiply x times 8, which we traditionally write with the constant first, the variable last, 8x. But we have now taken an expression that it didn't seem like we could do anything with and found a way to do something with it. Once you see how this works, I generally expect that writing things out, you will see something like 3x plus 5x and be able to immediately say, oh, that's 8x, without writing out the intermediate steps. This is one of the most important tools in all of mathematics, so it's been given a fairly straightforward name. It's called combining like terms. It is important to notice here that we need to have like terms. We need to have the exact same variables in each of the two things being added together, or this doesn't work. Consider another example. 3x squared plus 5x. If I tried to write this out using the process I had before, I could write it as x times, well, x times 3 is 3x. We have to multiply by another x because x times x is x squared. So trying to do this, there's nothing else we can do. These two terms are not like, so they cannot be simplified. Likewise, if I have something like 3x plus 5y, x and y are two different variables. These are not like, and there is nothing we can do to simplify this. In practice, generally, you don't have expressions where all of the terms are like. You will have expressions where there are a couple of different kinds of terms all mixed together. Consider here, sorry, I wrote that backwards actually. 3x plus 4y plus 5x minus 9y. Now with this expression, there's not a lot we can do, but if I make a very simple change, minus 9y is the same thing as plus negative 9y. Now, everything in this expression is addition. And we have the commutative and associative properties of addition. Technically speaking, this is a 5-step process, but no one ever writes out all of those steps. We can look at this bit of addition first, and we can swap the order in which it is written. Then we can use the associative property to evaluate this first and evaluate that, and then worry about the rest later. 3x plus 5x, those are like terms. We can combine them. 3 plus 5 is 8. 4y and negative 9y, those are like terms. We can combine them. 4 plus negative 9 is negative 5. Then we're left with 8x plus negative 5y. At this point, these are no longer like terms. There's nothing else we can do. All right. So using the distributive property, using the method of combining like terms, using the commutative and associative properties to rearrange a sequence of addition, using the definition of subtraction as the inverse of addition or the adding of a negative, we can rearrange expressions and take things where the order of operations tells us there's nothing we can do and turn it into something where there is something we can do instead. I'm going to wrap this video up here. As always, take a look at the practice problems, and I'll see you in the next video.